Hello, good morning everyone. So let's start today's session. In continuation with the last session, we are going to extend our discussion on closure of set of functional dependencies, and further on the similar lines we are going to look at the concept of closure of attribute set. So let's begin with closure of set of functional dependencies. So as we stated in the last session, we have been provided with the set of functional dependencies F for the relation schema R. It is possible to infer few of the functional dependencies logically by making use of this given set F. So set of functional dependencies, those can be inferred logically by the given set F, will form a new set, and that set is actually known as the closure of the set of functional dependencies. So once again I'll repeat, the set of all functional dependencies logically implied by the given set F is the closure of set of functional dependencies F, and this closure of F is denoted as F plus. To compute F plus, we have seen few rules. Those are known as the Armstrong's axioms. So if we use Armstrong's axioms, it is possible for us to logically come up with new functional dependencies based on the given F. So we have seen three such Armstrong's axioms. The first rule is reflexivity. So if beta is subset of alpha, then alpha determining beta is the valid dependency, and this rule is known as reflexivity. Second rule is augmentation. If alpha determines beta, then gamma alpha determines gamma beta. So we are augmenting the attribute or set of attribute towards both the sides of the functional dependency, and we come up with a new one. So this is called as augmentation rule. The third rule that we have seen is the transitivity rule. So if alpha determines beta and if beta determines gamma, then alpha determines gamma. So this is known as the transitivity rule. And we mentioned that Armstrong's axioms are sound and complete. Sound meaning Armstrong's axioms generate only functional dependencies those actually exist, and these rules are complete, meaning the Armstrong's axioms generate all functional dependencies that hold. Right? So we have seen these rules, and we have also seen one example in the last class. So let us proceed now with few more rules. So besides these three Armstrong's axioms, the basic rules, it is possible to have some additional rules as well. These additional rules simplify our manual computation of F plus. So what are those additional rules? Let us go through the additional rules other than Armstrong's axioms, and these rules can be developed by making use of Armstrong's axioms, right? So we can prove how we are coming up with these rules by making use of Armstrong's axioms, right? So these additional rules, first is the union rule. If alpha determines beta holds, and if alpha determining gamma also holds, then we may come up with a new functional dependency, that is alpha determines beta gamma. Meaning, if the determinant of the functional dependency, that means if left hand side of the functional dependency is same, then we may have the union of right hand side, and we may come up with a new functional dependency, alpha determining union of right hand side, that is beta gamma. So simple it is, right? So this rule is known as the union rule. Next is the decomposition rule. So what this rule says, if we are having a dependency like alpha determining beta gamma, then we may come up with new functional dependencies like alpha determining beta and alpha determining gamma. So here beta and gamma are the attributes or set of attributes. So if alpha is determining two sets of attributes, then individually we may decompose this right hand side, and we may come up with the functional dependencies like alpha determining beta and alpha determining gamma. So this rule is known as decomposition rule. Further, we may come up with the pseudo-transitivity rule. So what this rule says, see here, if alpha determines beta and gamma beta determines delta, then alpha gamma determines delta. See here, alpha determines beta and gamma beta determines delta. Then alpha gamma determines delta. So this is the pseudo-transitivity rule. And as I stated, all these rules can be proved by making use of the Armstrong's axioms, right? And why these additional rules are framed? To simplify the computation of F plus. In fact, by making use of Armstrong's axioms, it is possible for us to compute this F plus, no doubt, right? But to simplify this manual computation, if we make use of these additional rules, it is possible for us to expedite our work, right? And that is why we are having these additional rules, right? And as I stated, these rules can be inferred from Armstrong's axioms. I hope you must have understood all these rules, 3 basic Armstrong's axioms and 3 additional rules. So what are the Armstrong's axioms? First is the reflexivity. What is the second rule? Please pick up. First is the reflexivity rule. What is the second one?
Augmentation.
Augmentation, yes.
Transitivity.
Augmentation, and third is transitivity. And 3 additional rules are union, decomposition and pseudo-transitivity. Right? Now, let us proceed with one example so that you can understand how to make use of these rules. Assume that we are having this relational schema R with 6 attributes. So attributes of R are A, B, C, G, H, I. And we have been provided with this set of functional dependencies F. So what are the dependencies those we have? A determining beta, A determines C, CG determines H, CG determines I, and B determines H. These are the functional dependencies those we have, and this is our relation schema R. Now, what we are asked for, we want to compute few members of F plus. Right? So given F, we would like to compute F plus. but it is very difficult to compute all or to come up with all the members of F plus. So let us simplify our task. We want to come up with few members of F plus, right? And we are supposed to apply the Armstrong's axioms or the rules, those we know, right? So to come up with the members of F plus, how we are going to apply these rules, right? See, we may come up with a new dependency like A determining H. So how we are coming up with this new functional dependency that would be the member of our F plus, that is the closure of F. How we are computing this A determining H? See here, we have been given A determines B and we have been provided with other functional dependency B determines H. So if use of these two, A to B and B to H, then by applying the transitivity rule, we may come up with a new dependency like A determines H. Right? So this is a new member that we can add in our F plus. Right? Now, let us see one more. We are having here AG to I. AG to I. We are having new functional dependency AG to I. So how we have computed this AG to I? See, we have been provided with this A to C. So we are going to augment G to this functional dependency. So this functional dependency is being augmented with G. So we come up with AG to CG. Right? So we are coming up with AG to CG. Actually, this AG to CG is also the member of F plus. Right? Now, as we are having now this AG to CG and this functional dependency CG to I is given. So, if we make use of these two AG to CG and CG to I, by making use of transitivity, we may come up with AG to I. So, this can be added in our F plus. Are you getting me?
Yes, ma'am.
So, this is how we need to apply the rules and we should come up with new members of F plus. So, we are having here A to H, AG to I, even AG to CG is the member of F plus because we are augmenting here G with A to C, right? Now, let us see one more, CG to HI. CG to HI. So, how we are coming up with this? Anybody? How we are coming up with this CG to HI?
By union property.
Yes, correct. Very true. So, we are having two functional dependencies here, CG to H and CG to I. For these two functional dependencies, the left hand side is same. The determinant of the functional dependency is same, and that is why we may come up with CG to HI by union rule. Right? So this we can add. Similarly, if we look at this A to B and A to C, once again, if we apply union rule, that we may add is A to BC. So lots of different functional dependencies, those we may add in our F plus. Right? So you may have similar kind of questions in your exam. So given the relational schema and also the set of functional dependencies, compute the members of F plus. Though it is not possible manually to compute all the members of F plus, right? You are asked to compute few members, right? And by looking at and by applying the axioms, it is possible for us to come up with the new members. So I hope you must have understood the home adding few more members now. This is just one example. Right? So for the same relational schema with the same set of functional dependencies, please try to add few more members to this F plus. Apply the rules and come up with new members. Got it? May I proceed? Yes?
Yes, ma'am.
Now, let us look at a formal procedure for computing F plus. In the previous example, what we did, we randomly used the axioms or rules, those we were knowing, right? And we applied those rules to come up with new functional dependencies. But there is a predefined procedure for computing this F plus, or to compute the closure of the set of functional dependencies. So let us go through this procedure. So if we want to come up with the complete set F plus, we need to apply this process. So what we are going to do is, first of all, we are going to initialize our F plus with F. Right? So whatever is the set of functional dependencies F that is being provided. So initially we are assigning F plus equal to F. Right? And next we are going to repeat the process till our set F plus is changing. So if there is a change in F plus, we are going to repeat the process. But if there is no change anymore in F plus, then we are going to terminate our algorithm. Right? So what are the steps? Those we are going to follow. See here, for each functional dependency small f in F plus. So what is our F plus? Initially, it is the same set of functional dependencies F. So what we are going to do is, for each functional dependency in F plus, apply reflexivity and augmentation rules on F.
Then alpha determines beta.
Yes, if beta is subset of alpha, then we may come up with the functional dependency like alpha to beta. Right? So we need to use every functional dependency in our F plus, and we need to first check this rule. Right? And we may come up with the new functional dependencies. What next? We need to make use of augmentation rule. So what augmentation rule says? What is augmentation rule? Yes.
If alpha determines beta, then gamma alpha determines gamma beta.
Correct. So if alpha determines beta, then gamma alpha determines gamma beta. So this is the augmentation rule. So what we need to do is, we are picking up every functional dependency, we are applying the reflexivity rule, and also for that functional dependency we are going to apply augmentation rule as well. So how we are going to apply this? Suppose we are having the relation schema R, okay, with 4 attributes, say A, B, C, D. And let us assume that the first functional dependency that we are having is A to B. So we are picking up this functional dependency. Okay, and while applying the augmentation rule, what we are going to do is, see here, A to B we have. So we are going to augment every attribute, right, to this. So if we augment A towards both the sides of this functional dependency, then what we will get? We will get A to AB. Is that correct? functional dependency. Then what we are getting? AB determines B. Are you getting me? If I augment C to this functional dependency, what I am getting? I am getting AC determining BC. Similarly, I may augment C and I may come up with AD determining BD. Right? So this is how we are going to add the functional dependencies by applying these rules. Right? So in the first step, what we are going to do is, for each functional dependency in F plus, apply reflexivity and augmentation rules on functional dependency F and add the resulting functional dependencies to F plus. Okay. Now, what next? For each pair of functional dependencies F1 and F2 in F plus, if F1 and F2 can be combined using transitivity, then add the resulting functional dependency to F plus. What does this mean? Now, suppose we are having the functional dependency like A to B and B to C. So this is my F1 first functional dependency and F2 second functional dependency. So we are picking up the pairs of functional dependencies in F plus. Okay, and if it is possible to apply the transitivity rule, we are going to apply the transitivity rule and will be coming up with the new functional dependency like A to C. Right? So this is how we are going to add the functional dependencies by making use of this transitivity rule. Right? And we are going to repeat this process until there is some change in F plus. So after several iterations, what will happen? After several iterations, our F plus will remain unchanged. Right? So after adding all the functional dependencies in F plus, at some instance, our F plus will become like it will not change anymore. So at that instance, we are going to terminate. This is a formal way for computing this F plus by making use of Armstrong's axioms. We are having one more alternative procedure to compute F plus. We are going to talk about that procedure later. Right? But this is the first procedure that we may make use of for computing our F plus. Now, we know what are the Armstrong's axioms. We know how to compute this F plus. But actually, you should have one question in your mind. Why? Why we are doing all this? Why there is a need to compute F plus? So, I am going to provide you here the reason why we are computing this F plus. The main purpose of identifying the set of functional dependencies of a given relation is to specify the set of integrity constraints. I'll repeat, the very important purpose of identifying the functional dependencies for a given relation is to specify the set of integrity constraints that must hold on the relation. So, by making use of this F plus, it is possible for us to come up with these integrity constraints. And the most important integrity constraint that we are going to identify for the relation is the candidate key. So given a relation R with some attributes, always we need to impose upon the integrity constraints on this relation. So by making use of functional dependencies, we are actually providing these integrity constraints. And to come up with one of the most important constraints, that is the candidate keys. If we want to find out the candidate keys for this relation R, we need to make use of this F plus that we are computing. So F plus will help us to come up with the candidate keys for relation R. And one of the candidate keys we are going to pick up as the primary key for the relation. That is the most important constraint that we are having for our relation. Right? So, how we are going to determine this candidate key for the relation? Right? By making use of this functional dependencies. So, a set of attributes of relation R is a candidate key of R if and only if the set functionally determines every attribute of the relation. I'll repeat. A set of attributes of relation R is a candidate key of R if and only if the set functionally determines every attribute of the relation. What does this mean? Suppose I am having a relation schema R with 4 attributes, say A, B, C, D. Right? So, I may say that this A is my candidate key. When I am going to say that this A is my candidate key, if and only if this A determines all the attributes of R. So, A should determine A should determine B, A should determine C, and A should determine D. So ultimately, A should determine all the attributes A, B, C, D of my relation. If this is the case, then I may say that this is my candidate key for the relation. So if I am knowing all the functional dependencies those exist for this relation schema R, then it is possible for me to check for candidate keys of the relation. And that is one of the motivations why we are computing this F plus. Because F plus includes all the functional dependencies those exist for given relation. Right? So if I am having the set of all functional dependencies those exist, then it would be possible for me to come up with the candidate keys for the relation. Right? And candidate keys are actually providing the integrity constraint on the relation. That's very good. So let's proceed now with one exercise. You may have similar kinds of questions in your exam. Also, you may find similar kinds of questions in your competitive exam like GATE. Right? So, we are going to solve many such kinds of questions in this unit. So, this is the very first simple question. So, assume that we are having this set of functional dependencies like AB to C, C to D and D to A. So this is our set of functional dependencies F that is being provided. Right? And the relation schema R is A, B, C, D. So we are having 4 attributes in our relation and we are having these functional dependencies available with us. And the question is, what are the candidate keys of this relation? What are the candidate keys of this relation? So how we are going to compute the candidate keys? Right? So let us see the solution. We may come up with, so if we pick these 2 attributes A, B Okay, then we may come up with AB to A and AB to B by reflexivity rule. Right? So what my reflexivity rule says? If beta is subset of alpha, then I may have a dependency like alpha to beta. So A is subset of AB. So I may come up with AB to A. I may come up with AB to B. Right? So I am having now these two functional dependencies. AB to C is being provided. AB to C is being provided. Right? Now, what next I am going to do is I am having AB to C and also I am having C to D. I am having AB to C and I am having C to D. So, by applying transitivity rule, I may come up with this AB to D. Right? By reflexivity rule, I am having AB to A, AB to B. By transitivity rule, on A to C and CD to D, both are given in our F. Right? We may come up with AB to D. AB to C is already been given. So, AB is determining A, AB is determining B, AB is determining C, and AB is determining D. So, AB is determining all four attributes in my relation R. Are you getting me? AB is determining all the attributes of my relation R. Okay, so if AB is determining all the attributes in the relation R, I may say that AB, first of all, I may say that AB is my super key of the relation. But I want to find out the candidate key. So what we mean by candidate key of the relation? Candidate key is the minimal super key. What we mean by minimal super key? If there is no proper subset of this AB which also determines all the attributes, then we may declare that this AB is my candidate key. Right? So far we have found out that AB is our super key. So let us try to find out whether A only determines all the attributes and whether B only determines all the attributes, because these are the subsets of this AB. So if I consider only A, then I may find out that A only will not determine all the attributes A, B, C, D of my relation. Similarly, only B cannot determine all the attributes of my relation, that is A, B, C, D. So B cannot determine all the attributes. A also cannot determine all the attributes. And that is why I may declare that AB is a candidate key of the relation R, because it functionally determines all the attributes of my relation. Right? And there is no proper subset of AB that also determines all attributes. So only A cannot determine all attributes, only B also cannot determine all attributes. But if I am having this combination AB, it will determine all the attributes of my relation. So I may declare that AB is my candidate key. Are you getting me? Yes?
Yes, ma'am.
So, similarly, find out if any other candidate keys exist. for this particular relation given the set of functional dependencies. Check it out. We have identified one candidate key, that is AB. I'm giving you this as the homework, right? So in the next session, you should come up with the solution for this problem. As we have found out AB as one of the candidate keys, find out if any other candidate keys are also there for this relation, right? So this is the homework for you. Okay, so let us proceed now with the next concept, and that is closure of attribute sets. So we have talked about the closure of set of functional dependencies. So we talked about F plus, and now we are going to discuss the closure of attribute sets. So what we mean by closure of attribute sets? So given the set of attributes alpha, we can define the closure of set of attributes alpha given the set of functional dependencies F. This set is denoted as alpha plus, right? And this set is the set of attributes those are functionally determined by alpha under the given set F. What does this mean? See, alpha to beta is in my F plus. What it indicates? Alpha determines beta. What it indicates? Beta is subset of alpha plus. So what is this alpha plus? Alpha plus is the closure of alpha under the given set F. And this alpha plus denotes the set of attributes. Those are functionally dependent, or those are functionally determined. By alpha. So alpha plus includes all those attributes, those can be determined by alpha. That's all. Okay, so we are having very simple algorithm to compute disclosure of attribute sets. So let us go through this algorithm. So in this algorithm, we are going to compute the closure, that is alpha plus closure of attribute set. So we are going to initialize our result with the given alpha. Right? Now, what we are going to do next is we are going to follow certain steps. So what result we are going to iterate through. Once we do not have any change in our result, we are going to terminate. So what we are going to do, for each functional dependency in F, for each functional dependency of the form beta to gamma in F, we are going to check whether this left hand side of the functional dependency, that is beta, is subset of our result. If beta, that is left hand side, is subset of the result, then what we are going to do is we will be having the result updated as result union the right hand side of the functional dependency. So if beta is subset of result, then result gets updated as result union right hand side of the functional dependency. And we are going to iterate through for all functional dependencies, those we have in F. And ultimately, what we are getting is alpha plus, that is the closure of alpha under F. So let me illustrate this with one simple example so that you can understand it. right? So we are having this relation schema R with 6 attributes A, B, C, G, H, I, and we have been provided with these functional dependencies. Okay, now what we want is we want to compute AG plus. We want to compute AG plus. So we want to compute the attribute set closure for this AG. So here my alpha is AG. And what I want to compute alpha plus. That means I want to compute this AG plus. So we are having this algorithm with us. So whatever algorithm says the first step, result is assigned to alpha. So what we are going to do is our result is our alpha. That means initialize result with alpha. We want to compute AG plus. So we are having here result equal to AG. Okay, now what next? We are going to pick every functional dependency from F and we are going to follow this step. So let us pick this first functional dependency A to B from our F. Now let us find out that this left hand side is subset of my result. So what is my result? Result is AG. So whether this left hand side, that is A, is subset of AG, whether A is subset of AG, yes, whether A is subset of AG,
Yes,
yes,
ma'am.
it is,
Yes, ma'am.
yes. So if A is subset of AG, what we need to do is we need to update our result such that result equal to result union gamma. That means the right hand side. So now my result gets updated. So earlier I was having AG as the result. So this right hand side B is being added in my result. So I am having AG union the right hand side, that is B, AG union B. So I'll be having result equal to ABG. Right? Now, what next I'm going to do? I'm going to pick the next functional dependency. So A to C. So once again, I'll check whether this left hand side A is subset of my result. So now my result is ABG. Whether A is subset of my result, whether A is subset of ABG,
Yes.
Yes.
yes. So what I'll do, I will have the union of old result with the right hand side of my functional dependency. So this is union, ABG union C. So my new result would be ABCG. Correct? Are you getting me?
Yes,
Yes,
ma'am.
ma'am.
So let us pick now the next functional dependency, CG to H. Okay, now once again the same procedure we are going to follow. So whether CG is the subset of ABCG, that is the earlier result. So CG is subset of ABCG, yes. So what we are going to do, old result, that is ABCG union the right hand side of the functional dependency, that is H. So the new result would be ABCGH. Let us check with the next dependency, CG to I. So CG to I, we are checking now whether CG, that is the left hand side, is subset of my result. So whether CG is subset of ABCGH. Yes, it is. So what we are going to do is we are having here old result, that is ABCGH union the right hand side of the functional dependency I. Okay, so what we are getting is ABCGHI. Now we may check the next functional dependency B to H. Right? Now obviously What I need to check is whether B is subset of A, B, C, G, H, I. And yes, obviously yes. So we are going to have the union. But see here, if I am having the union, I am not going to change my result. My result will remain same. Right? And that is why we are going to terminate here. So our AG plus would be A, B, C, G, H, I. So closure of this set of attributes AG, that is AG plus, is given as A, B, C, G, H, I. Right? Got it? If you have any doubts, please let me know. Yes. Yes. Any doubt? Any doubt?
No, ma'am.
Fine. So this is how it is possible for us to compute the attribute set closure. So in the next class, we are going to see what are the uses of this attribute closure. Why actually we are going to compute this attribute set closure and how to make use of this closure. Right? So in the next class, we are going to discuss the uses of attribute set closure. Right? So let's conclude today's session. Thank you.